I'm going to talk about AI-powered, just-in-time per-title encoding, which is a little bit of a word soup of a title. If you haven't met me before, hey, I'm Phil. I'm head of innovation at Mux. I previously ran the Mux video product for the last 3 years. I've been in streaming about 15 years, which I think is probably about average for this room. I've worn about every hat at Mux in the last 7 years, product engineering, support, marketing, you name it, I've kind of done it. I now mostly focus on AI products, accelerated products, early stage things we just want to kind of try and get out the door. I also run London Video Tech, and I also run this other thing that I think I was keeping count has been mentioned 5 times, which is a conference called DMUX, which is back in San Francisco this year. There's a couple of little things you need to know before I tell you interesting things about our per-title encoding. First one is what Mux Video is. Mux Video is video infrastructure for a general developer audience. It's not for media companies like a lot of you build for. It's simple, it works for live, it works for VOD, it's very affordable, scales as you grow. But we work with customers like Patreon, Synthesia, Vercel, Yelps, places like that, people who are not at their core media companies, they are tech companies, so it's a very different experience. Mux Video uses just-in-time encoding, right? So 80% of the videos that come to Mux, it's actually more like 90%, don't get encoded up front. They get transmuxed, put into storage, and then as a viewer watches them, we encode the segments on the fly and deliver them to the user. That means that the performance of our encoding feels pretty great. You can do an hour in like 60 seconds of processing. So we give a lot of value to customers through that, especially UGC customers who just want stuff to be instantly available when it's uploaded to a platform. The ingest workflow is actually kind of simple. We download the input file, we just check its structure, so we check the codecs, resolution, GOP structure, bit rates, things like that, whether it's compatible with a just-in-time encoding solution. If it isn't, we throw it for a transcode first. If it is, we just host it. We transmux it into an MP4 and store that media. What we're trying to avoid is a full decode because it's slow, right? Per-title encoding, raise your hand if you know what per-title encoding generally is. Okay, won't go too deep on this as we're time traveling. Fundamentally, not every video is the same. If you encode every video the same way, you're wasting quality on some and you're wasting bitrate on others. Netflix coined this in 2015. There's been tons of research in the industry over the last 10 years, over 10 years now, on this topic. Hey, Phil, haven't you talked about per-title encoding before? Yes, I have. We first built per-title encoding in 2018, 2019. I've talked about it a few times. I actually think there's a chance I've talked to Mahai Video about it as well. Our first version decoded the media at ingest, used a neural network to predict a convex hull, and generated a bitrate ladder for the content based on that convex hull. This is a pretty traditional way to do per-title encoding. A little bit of machine learning to work out what convex hull to use, but kind of pretty common approach. It worked okay most of the time. Sometimes it wasted bandwidth, which is not ideal. The real bad problem was sometimes it just made really wrong decisions. We didn't have good observability to see when it made bad decisions. But it was also like really complex, very high maintenance, very high overhead, and it included created a full decode cycle when we were creating content. So slowed the prediction at ingest time. So you're kind of going to say to me, but Phil, those are just bugs. Why didn't you just go fix the bugs? Well, I don't know if you remember, but 2019, 2020, the world went kind of weird for a little bit there. The world, certainly for us, was a hyperscale moment where everyone was doing video on the internet, right? So we had to focus on reliability, scale, live-centric workflows. So our per-title product just didn't get a lot of love in that time. Lots of other people moved on from our company to other companies, some of them in the room. And so then in the post-pandemic correction that we all saw, we had to look at other things as well. So we did it again. Last year before last as well, we started building per-title again. Well, really cool thing about kind of getting something wrong once is you get a really good set of requirements for the first time you do it. So here's our requirements. First of all, measuring perceptual quality just on an ongoing basis. Not slowing down ingest by any meaningful amount. Yeah, we can get away with a couple of %, especially on the outliers, but not spending like a full decode is kind of our desire there. Lean into AI. Turns out AI is a good thing, and we're all doing AI now. Having really strong guardrails against getting it really badly wrong. and like a simple maintainable architecture, something we can iterate on. But then like one of the big learnings was just not every customer wants to make the same trade-offs, which is really important when you're building per title, because a lot of per title approaches assert solve it once, it's solved for everyone. Turns out not to be true. So, measuring perceptual quality and bit rates on every single piece of media. So we wanted to measure for every just-in-time encode we do, which is hundreds of millions of segments a month. So step one was picking a perceptual quality measure. Could use SSIM, VSNR, PSNR, VMAF, or any of kind of 100 other derivatives. VMAF is like the gold standard, but that doesn't work at hundreds of millions of segments per month scale. It costs us far too much. It'd take far too much time. That's not feasible. Cool thing is X264 gives you in-frame SSIM, so it actually kicks that information directly out of the encoder, so it's like free, like we're not spending anything to get that, but as you all know, SSIM is imperfect. But it's a good starting point. Then you've got to put that data somewhere. We put the short-term analysis into Grafana. That's our observability stack of choice. And then our long-term data goes into Snowflake so you can do complex ML things on it in the future. Then we got to put those bitrate piece of information in the same place. So what you want to do is ultimately mesh the quality data you've got and the bitrate data you got to train an AI algorithm to do the right decisioning there. Looks like this in Grafana. You might not be able to see too much of it. The kind of the interesting thing here is like the way some of the lines stop on like the SSIM measure on the left. That's because those segments haven't been watched. Right, so just-in-time encoding architecture. If nobody watched the segment at a given quality, we actually don't get quality data or bitrate data for it, which is a little bit of a mixed bag, but kind of interesting. We actually didn't end up using SSIM. We actually ended up using CRF. Now, this is a weird one because CRF is not a quality measure, right? CRF is just a rate control measure. We use constrained CRF at the encode, which has benefits and downsides. But the encoder tells you, when you tell it to use CRF, what CRF it hit, right? Did it manage to get, if you say do CRF 19, but it hit CRF 20, you were constrained, right? So you can actually use the data straight coming back from the encoder from how the rate control behaved instead of a perceptual quality measure. For us, we then trained effectively a large set of analysis across all our customers and said, okay, if you want to increase the CRF by a point, you can decrease your bit rate by 13%, and the inverse. If you want to increase your CRF by a point, 30%, decrease your CRF by a point, you need to increase your bit rate by 13%. Your measures will differ, your codecs will differ, etc. But it's a very generalized model for our customers. Cool. Now, we don't want to slow down ingest by a meaningful amount. This is hard, because it's quite hard to understand what's in video without actually decoding it. But the core here is you don't need to care about what's in the video. You need to care about how complex the video is. And that's kind of a different question, right? So how can we predict complexity without doing a full decode? Our solution was to look at quantization parameters. Raise your hand if you know what a quantization parameter is. Cool, great, that's exciting. Last time I did this talk, I had to explain a lot about quantization parameters. This is like how much a given macro block was compressed, right? So H264, that's 16 by 16 block. And this is a trade-off between quality and compression efficiency. So what we're doing is we're looking at how the last encoder behaved. So if we've been given a piece of media from an iPhone, we're looking at quantization parameters that the iPhone picked when it was encoding that video as an impression of how hard that encoder was working at the time when it compressed that macro block. It makes a pretty good proxy for complexity, as it turns out. Yes, disclaimer, different codecs use macro blocks differently, use quantization parameters differently. That's a whole other talk in itself, honestly. When you combine this information with the size of a macro block in bytes, you get kind of 4 outcomes. One is it's a small byte with a low QP. Probably this was low complexity, so the data still looks good without having to compress it. If it's a small byte with a high quantization parameter, this was really compressed, so you got to choose between either it was like unimportant, it was just a background, or you're hitting a bitrate limit. If it was big and it had a low QP, uncompressed, unimportant, or we had bandwidth to waste, or if it's big and had a high QP, this was really compressed and the encoder was working really hard, so this was probably a problem area where you were constrained on quality. We end up running this analysis on every piece of media that comes in, spits out a JSON blob that looks like this, grouped by P frames, B frames, I frames, and then an average across everything with the quality and the byte size of every block in it. We called it SSQP, which I'll admit was a backronym, Statistically Sampled Quantization Parameters. Only looks at frame structure, not content, just trying to interpret the intent of the encoder that came before us. Cool. Great. We've now got quality information. We've now got a way to get metadata about complexity without having to do a full decode. Now we need to do some AI on it. So the great thing is we've now got two big data lakes, right? We've got this data lake of information about quality. We've got this data lake of information about bit rates. We need to put that together and train a model that can tell us how to manipulate one based on the other. AI turns out to be just really good at this. It's a problem that's pretty well solved. This is more traditional machine learning than it is like giving it to an LLM, right? I'm not going to go send this to ChatGPT and say, give me what my structure should look like. I'm going to train a model specifically for this. We use a random forest regression model, pretty simple, traditional machine learning. Basically, it's a ton of decision trees and then takes an average across those decision trees to give you a prediction of a final result. It's good for kind of nonlinear relationships in data, so it works well for this use case. If you were doing it today, I'd maybe use a SVM instead, but that has challenges when it comes to data it hasn't seen before. So there's upsides and downsides of both approaches here. Training, it's kind of simple. We use a product called Hex, which is kind of a Jupyter notebook on steroids. We use sklearn random forest regressor, which is just kind of in your standard Python toolkit of training machine learning models. Kicks out a horrible-looking PPML model that I opened in a text editor the other day and was horrified by it. And all that just drags data in from our Snowflake instance. During ingest, not too much changed here. We extract the SSQP, predict a top rendition, convert it to multipliers rather than just pure bit rates. Multipliers are really important because it lets you change your underlying architecture of your adaptive bitrate ladder without changing kind of your whole stored data about what bit rates to use. This was an improvement over the previous version, which stored actual bit rates. And then during playback, you just apply them. So what it looks like, it just kind of gives you a JSON blob for basically a proposed multiplier. Then we do some maths to make an effective multiplier just to clean up the data a little bit. And then obviously that's kind of the definition of the ABR ladder for that content. Cool. We need guardrails. Great. We put caps on both ends. This is really important because sometimes the model is going to say you need 10 times the bit rate to make this look consistent. You probably shouldn't do that, right? For two reasons. One, it wouldn't be viewable. Other reason, hey, you care about COGS, right? We're a media company. We care about COGS. Everyone in this room cares about COGS, I'm sure. But we also have a minimum clamp as well. That minimum clamp exists to screen recording content to make sure that it retains its sharpness, because otherwise the complexity analysis generally says it's really low. So we need to clamp at the bottom to try and handle screen recording content well. Great. Is it simple? Is it architecturally simple? Yeah, it's pretty good. Not too much change to our JIT pipeline. It's also got a really safe fallback approach. If you don't get an analysis, you don't get a prediction, you just don't do per title encoding. Pretty simple. Pretty low maintenance. We just have to train new data sets every now and then. That Hex workbook, though, has gotten pretty brutal at this stage, and this is where 99%, it keeps going, this is where 99% of complexity ends up in this, but you don't run it that often, you don't make that many changes on it, but we can run this, we could run this every week, we could run this every day if we really wanted to. It's more of a question of when do you think you've got something meaningfully different from the already kind of billions of data points you already have. We're getting hundreds of millions of new JITs a month, so it's pretty reasonable to say this is running on billions of data points of analysis. Is it cost effective? Yeah, actually, it's pretty cost effective. Storing a PQ data certainly has cost, but our Snowflake scale is also pretty big, so it's kind of noise. Training cost is negligible, takes half an hour to run the workbook. That's also not done that frequently, so it doesn't really matter. Execution cost, negligible. Does it save money overall, though? Good question. I'll get to that one. I'm pretty much there. The really interesting one, though, we wanted to apply in here is not every customer wants the same thing, right? A one-size-fits-all per title approach is a bit of a myth, right? It might be true if you're Netflix, because you have one quality goal, you just want the highest possible quality, right, for a given bit rate that you're comfortable doing. Our customers don't necessarily want that, right? We've got customers who are building social scrolling apps that do not care about quality, really meaningfully, like has to be good enough, but care an awful lot about cost. And then we have customers at the complete opposite end of the scale who care only about quality and not so much about cost. So trying to make a per title model that applies to all of those at once actually doesn't work, certainly for our customers. We ended up building 3 quality targets effectively. And this is effectively that knob between quality and cost. So it's a good, better, best. If you've ever packaged a product, I'm sure you've seen this from a pricing perspective. We have a good quality, which is free encoding, very cost effective. You have better and a best, which is more expensive. So does it work? We ticked all those things off. It must be fine, right? Everyone's targets for per title are different. You can target increasing quality for the same bitrate. You can target decreasing bitrate for the same quality. Or you can do a little bit of both, right? You can be in the middle of this. We are trying to be in the middle of this, especially when conjoined with the good, better, best packaging of the quality of the product. So we ended up with an average bitrate reduction of 12%, an average SSIM increase of 0.0005%, 75% of ingests do not experience any slowdown of using per title. And fundamentally, and as a product guy for a lot of my life, when combined with quality options for the customer, quality complaints went away. So we saved money, quality complaints went away, we're happy with that outcome ultimately. Here's what it kind of looks like as a graph. These are bit rates, so P90 bit rate went up, right, is what you'd expect. Some videos we were under-guessing on the bit rate needed. The P10 went down because we were overspending on bit rate, and the average went a little bit down along with the P50. And the quality went up. Again, you can see that kind of at the bottom end, we expect these to, we hope these converge a little bit, which is like, hey, we were doing bad quality before, it's coming back together, and the same on the other end as well. I'm over time, I know, sorry. If you want to ask me questions async, philipmonks.com or Video Dev Discord.
Thanks, Phil.